NENOMATICA, where mathematics meets YouTube excellence. Welcome to this math video, where we'll prove an important algebraic identity. Let's begin with our example. We'll prove the following statement. For all a and b in the set of real numbers, the product of a plus b and a minus b equals a squared minus b squared. Now, let's begin the proof. We'll use algebraic manipulation to show that this identity is true. Let's start with the left side of our equation. A minus b times a plus b. Notice that I've rearranged the factors compared to our original statement, but this doesn't change the result since multiplication is commutative. We'll use the distributive property to multiply these binomials. This is sometimes called the FOIL method. Multiply first terms, outer terms, inner terms, and last terms. So we get a times a plus a times b minus b times a minus b times b. Now let's simplify each term. We get a squared plus ab minus b a minus b squared. Since multiplication is commutative, a times b equals b times a. So we can rewrite ab minus b, a as ab minus ab, which equals 0. Let's group the middle terms. We have a squared plus the term ab minus b squared. The middle term ab minus ab equals 0. So we have a squared plus 0 minus b squared. The additive identity property tells us that adding 0 to any number gives the same number. So we get our final result, a squared minus b squared. Therefore, we have proven that for all real numbers a and b, the product of a plus b and a minus b equals a squared minus b squared. This is an important algebraic identity known as the difference of squares formula. Let's summarize what we've learned. First, we applied the distributive property to expand the product of two binomials. Then, we used the commutative property of multiplication to rearrange terms. Finally, we simplified to get our final result. This identity is useful in many areas of mathematics, including factoring, simplifying expressions, and solving equations. Welcome to this math tutorial, where we'll learn about solving algebraic expressions using the difference of squares formula. The difference of squares is a special formula in algebra that helps us expand or factor expressions. The general formula states that a squared minus b squared equals a plus b times a minus b. Let's look at our first example. We want to find the result of the expression 2a minus 3 multiplied by 2a plus 3. We can immediately recognize this as the factored form of a difference of squares. In this example, we have the pattern a plus b times a minus b, where a equals 2a and b equals 3. According to the difference of squares formula, this equals a squared minus b squared. So we get 2a squared minus 3 squared. Let's calculate this further. 2a squared equals 4 squared, and 3 squared equals 9. So our final result is 4a squared minus 9. So the final answer to our first example is 4a squared minus 9. Let's look at our second example. We want to find the result of the expression 2x minus 3y multiplied by 2x plus 3y. Similar to the first example, we can recognize this as a difference of squares pattern. Here, a equals 2x and b equals 3y. Using the difference of squares formula, we get a squared minus b squared, which is 2x squared minus 3y squared. Let's calculate this further. 2x squared equals 4x squared, and 3y squared equals 9y squared. So our final result is 4x squared minus 9y squared. So the final answer to our second example is 4x squared minus 9y squared. Now, let's move to our third example. We want to find the result of the expression x squared plus 1 multiplied by 1 minus x squared. First, let's rewrite this expression to match our difference of squares pattern. Notice that 1 minus x squared is the negative of x squared minus 1. So we have x squared plus 1 multiplied by negative of x squared minus 1. Now we can see this is almost in the form of a plus b and a minus b, except the order is reversed. Let's rewrite it differently. We have 1 plus x squared multiplied by 1 minus x squared. Now we can clearly see this follows our difference of squares pattern, where a equals 1 and b equals x squared. Using the difference of squares formula, we get a squared minus b squared, which is 1 squared minus x squared squared. Let's calculate this further. 1 squared equals 1, and x squared squared equals x to the 4th power. So our final result is 1 minus x to the 4th. So the final answer to our third example is 1 minus x to the fourth power. Let's summarize what we've learned today. We use the difference of squares formula, which states that a squared minus b squared equals a plus b times a minus b. We applied this formula to solve three different examples. Example 1, 2a minus 3 times 2a plus 3 equals 4a squared minus 9. Example 2, 2x minus 3, y times 2x plus 3, y equals 4x squared minus 9y squared. Example 3x squared plus 1 times 1 minus x squared equals 1 minus x to the fourth power. Remember, whenever you see expressions in the form of a plus b times a minus b, you can quickly calculate the result using the difference of squares formula. We have the expression 3a squared minus b squared times 6a squared plus 2b squared. We need to simplify this expression step by step. Our first step is to factor out common terms from both expressions. Looking at the second bracket, 6a squared plus 2b squared, we can factor out a 2 to get 2 times 3a squared plus b squared. Next, we apply the distributive property to multiply the expressions. We can rewrite our expression as 2 times 3a squared minus b squared times 3a squared plus b squared. Now, we recognize that we have an expression in the form of a squared minus b squared times a squared plus b squared, which is a difference of squares pattern. This simplifies to a to the power of 4 minus b to the power of 4. Let's simplify the powers in our expression. 3a squared squared equals 9a to the fourth power, and b squared squared equals b to the fourth power. Finally, we distribute the constant 2 to get our final answer. 2 times 9a to the fourth minus 2 times b to the fourth, which equals 18a to the fourth minus 2b to the fourth. Now, let's move on to our second example. We have the expression a squared minus b squared squared times a squared plus b squared squared. Let's solve this step by step. First, let's recognize the pattern here. We have the square of a difference times the square of a sum, which can be rewritten as the square of the product of a difference and a sum. Now, we recognize that a squared minus b squared times a squared plus b squared is a difference of squares pattern, which simplifies to a to the fourth minus b to the fourth. Finally, we expand the square using the formula a minus b squared equals a squared minus 2ab plus b squared. In our case, a is a to the fourth power and b is b to the fourth power. Let's simplify the powers. A to the fourth squared equals a to the eighth power. B to the fourth squared equals b to the eighth power. For our third and final example, let's look at the expression a to the 20th power minus a to the 10th power times a to the 20th power plus a to the 10th power. This is directly in the form of a difference of squares. We can apply the formula a squared minus b squared times a squared plus b squared equals a to the fourth power minus b to the fourth power. Now, let's simplify the powers. A to the 20th squared equals a to the 40th power. A to the 10th squared equals a to the 20th power. We need to simplify the expression 2x minus y times 2x plus y times 4x squared plus y squared. Let's break this down step by step. First, we'll apply the difference of squares formula to the first two factors. The difference of squares formula states that a minus b times a plus b equals a squared minus b squared. So 2x minus y times 2x plus y equals 2x squared minus y squared, which is 4x squared minus y squared. Now for the next step, we'll apply the difference of squares formula again. Notice that the expression 4x squared minus y squared times 4x squared plus y squared also matches our difference of squares pattern. Here, a is 4x squared and b is y squared. So we get 4x squared squared minus y squared squared, which equals 16x to the fourth minus y to the fourth. So our final answer is 16x to the fourth minus y to the fourth. Let's reflect on what we did. We recognized that we could apply the difference of squares formula twice to simplify this expression. Let's move on to our second example. We need to simplify the expression a minus 3 times a squared plus 9 times 2a plus 6. Looking at this expression, let's first factor out the common factor in the third term. We can see that 2a plus 6 can be factored as 2 times a plus 3. So our expression becomes a minus 3 times a squared plus 9 times 2 times a plus 3. Now, we notice that a minus 3 and a plus 3 can be rewritten using the difference of squares formula in reverse. Specifically, a minus 3 times a plus 3 equals a squared minus 9. So our expression becomes 2 times a squared minus 9 times a squared plus 9. For our final step, we'll apply the difference of squares formula once more. We have a squared minus 9 times a squared plus 9, which follows our pattern with a squared and 9. This gives us a squared minus 9 squared, which is a to the fourth minus 81. Multiplying by 2, our final answer is 2 times a to the fourth minus 81, which equals to a to the fourth minus 162. Let's summarize what we've learned. Counterclockwise arrows button, we've seen how to simplify complex algebraic expressions by applying the difference of squares formula. Sparkles, the key formula we used, is a minus b times a plus b equals a squared minus b squared. Light bulb, we can apply this formula multiple times when we have nested expressions. Direct hit, the strategy is to identify patterns that match our formulas and apply them step by step. We need to expand the expression a minus b plus c multiplied by a plus b minus c. In our first step, we'll rewrite this expression to highlight a difference of squares pattern. We can rewrite this as a minus quantity b minus c multiplied by a plus quantity b minus c. Now, we can apply the difference of squares formula. Remember that a squared minus b squared equals a plus b times a minus b. In our case, we have a minus quantity b minus c times a plus quantity b minus c, which gives us a squared minus the quantity b minus c squared. Next, we need to expand the squared term b minus c squared. Using the square of a binomial formula, we get b squared minus 2bc plus c squared. Now, we need to distribute the negative sign to the terms inside the parentheses. When we distribute the negative sign, we get a squared minus b squared plus 2bc minus c squared. So our final answer is a squared minus b squared plus 2bc minus c squared. Now, let's move on to our second example. We need to calculate a squared minus 2a, quantity squared, multiplied by a squared plus 2a, quantity squared. First, we'll rewrite this as a power. We can express this as the product of a squared minus 2a and a squared plus 2a, and this entire product is squared. Now, let's focus on the inner product. We have a squared minus 2a multiplied by a squared plus 2a. This is a difference of squares pattern where we can use the formula a squared minus b squared equals a minus b times a plus b. Here, a squared is our a term and 2a is our b term. Let's simplify the powers inside the bracket. A squared squared equals a to the fourth, and 2a squared equals 4a squared. Now, we need to expand the square of this binomial. Using the square of a binomial formula, a minus b squared equals a squared minus 2ab plus b squared. We can expand a to the fourth minus 4 squared, quantity squared. Let's simplify each term in this expression. A to the fourth squared is a to the eighth. 2 times a to the fourth times 4a squared is 8a to the sixth. And 4a squared squared is 16a to the fourth. So our final answer is a to the eighth minus 8a to the sixth plus 16a to the fourth. We need to simplify the expression a plus b minus c squared times a minus b plus c squared. Let's work on this step by step. First, we'll rewrite the expression to make it easier to work with. We can rewrite this as a plus b minus c squared times a minus b minus c squared. Next, we'll use the formula for the difference of two expressions. Note that for the expression a minus b minus c, we can distribute the negative sign to get a minus b plus c. Now we can use the formula for the difference of squares, which states that a squared minus b squared equals a plus b times a minus b. In our case, we have a plus b minus c times a minus b minus c, which is a squared minus b minus c squared. We want to expand the expression a squared minus b minus c squared, all squared. Notice the entire expression is squared, and inside we have a squared minus the quantity b minus c, also squared. In step 1, we'll apply the binomial square formula. The formula states that the square of a difference equals the square of the first term, minus 2 times the product of both terms, plus the square of the second term. For step 2, we'll expand the first term, where a squared squared becomes a to the fourth power. We'll also expand the last term, where b minus c squared, all squared, becomes b minus c to the fourth power. In step 3, we need to expand the expression b minus c squared. Again, we'll use the binomial square formula for a difference, where b minus c squared equals b squared minus 2bc plus c squared. For step 4, we'll multiply through the middle term. We distribute a squared to each term inside the parentheses. This gives us a to the fourth power, minus 2a squared b squared, plus 4a squared bc, minus 2a squared c squared, plus the square of b squared minus 2bc plus c squared. Now for step 5, we need to expand the last term, which is b squared minus 2bc plus c squared, all squared. We'll use the formula for squaring a trinomial, which gives us several terms. In step 6, we'll simplify the expressions in the last term. b squared squared becomes b to the fourth. Negative 2bc squared becomes 4b squared c squared. c squared squared becomes c to the fourth. 2 times b squared times negative 2bc becomes negative 4b cubed c. 2 times b squared times c squared becomes 2b squared c squared. And finally, 2 times negative 2bc times c squared becomes negative 4bc cubed. Finally, in step 7, we'll remove the brackets and combine like terms. Notice that we have 4b squared c squared and 2b squared c squared, which combine to give us 6b squared c squared. So our final expanded expression is a to the fourth power, minus 2a squared b squared plus 4a squared bc, minus 2a squared c squared, plus b to the fourth power, plus 6b squared c squared, plus c to the fourth power, minus 4b cubed c, minus 4bc cubed. This is our complete expansion of the original expression. Now, let's move on to our second example. We need to simplify the expression a plus b minus c plus d times a minus b minus c minus d. Let's approach this systematically. First, we'll rewrite the expression by grouping terms. We can rewrite this as a minus c plus b plus d times a minus c minus b plus d. Now we can apply the difference of squares formula, which says that a plus b times a minus b equals a squared minus b squared. Now, let's expand both of these squared terms. For the first term, we'll use the formula for the square of a difference. A minus c squared equals a squared minus 2ac plus c squared. For the second term, we'll use the formula for the square of a sum. b plus d squared equals b squared plus 2bd plus d squared. Now, we'll distribute the negative sign to the second parenthesis. Our final answer is a squared minus 2ac plus c squared minus b squared minus 2bd minus d squared. We can rearrange this to get a squared minus b squared minus 2ac minus 2bd plus c squared minus d squared. In summary, we've worked through 2 different algebraic expressions step by step. For the first problem, we simplified a plus b minus c squared times a minus b plus c squared. For the second problem, we simplified a plus b minus c plus d times a minus b minus c minus d. In both cases, we used algebraic techniques such as factoring, difference of squares, and expanding expressions to arrive at our final answers. These techniques are essential for simplifying complex algebraic expressions. Remember, when faced with complex algebraic expressions, breaking them down into smaller, manageable steps using these fundamental algebraic techniques will help you solve them systematically. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.